Okay, now we see another type of biasing for this BJT, which we call it as potential divider biasing. The main advantage of this over the fixed bias is the voltage at VBE will not be floating, but it will be having a definite voltage which will be Vx here, which we're going to find out okay, what is the value of Vx. And this is a potential divider bias. Why the name potential divider is coming is, whatever voltage that is Vx we are writing here is derived out of this VCC. So when you have two resistors coming in series, we know that when you have two resistors R1 and R2, if it is connected to VCC and this is grounded, if you want to know what is the voltage at Vx, if you say this is current I, then Vx is actually equal to the drop across this resistor R2, which is nothing but I into R2. Then what is I? I is equal to overall voltage difference, that is VCC, divided by the overall resistance. So resistance is R1 plus R2. This is current I, this is R2. So what is Vx now here? Vx is equal to okay, now this VCC is actually 2.5 volt. It is 2.5 into 80k divided by 170k plus 80k. So this is my voltage. So which will be 0.5 into 80 divided by 250, which is 0.8 volt. Now that's the voltage at this point. Now we cannot take this as VB, so we cannot take this as VB, so you cannot continue with this as VB. So what is VB now? So now we have to use the concept of Thevenin voltage and Thevenin resistance. Even though this is, you are getting 0.8 volt, but we know that every voltage source or a current source is having some voltage amplitude. It can be DC, it can be AC. It will also have an associated source resistance of that source. So likewise, this potential Vx also has a resistance associated with that source. Now that resistance associated is nothing but R Thevenin. So there is a R Thevenin and there is a V Thevenin associated with this potential divider. What is R Thevenin, V Thevenin? If you stand here and look towards this side, whatever voltage that you see is called as V Thevenin. Whatever resistance that you see towards this is R Thevenin. So whenever you are seeing towards this R Thevenin, you should not consider this. So in such case, this and this, when I say don't consider this, treat this as ground. When I treat this and this as ground, if you are looking into this, it looks like this. So this is how it is looking. This is grounded, this is also grounded. You are standing here and looking towards this side. So this ground and this ground is same, means they actually come parallel. So this is 170k, this is 80k. When 80k and 170k come in parallel, so resistance looking towards the source is nothing but 80k in parallel with 170 kilo ohm, which is nothing but 1 over 80k plus 1 over 170k whole inverse. So which is nothing but R Thevenin. You can write it as 80 inverse plus 170 inverse whole inverse is 54.4 kilo ohm. 54.4 kilo ohm is R Thevenin. What is V Thevenin? V Thevenin is this only. So this is V Thevenin. So now, how do you replace this entire circuit now with R Thevenin, V Thevenin? So this potential divider is now replaced by a V Thevenin and an associated resistance, which is R Thevenin. So Thevenin is a scientist who actually found all these concepts way back in maybe 78 years ago, maybe more than that. So this is how it is looking. So this is what VCC, which is 2.5 volt. This is VThevenin, which is derived out of R1 R2 from this VCC, which is now 0.8 volt. And how much is this? This is 54.4 kilo ohm, correct? Now this is RC, which is nothing but 5k here, 5k you have. Now what is the equations you have? You have all these equations still valid. Is is equal to 1 e power minus 17, beta is equal to 100, and this is the value of IC in terms of VB and IS. Okay, one more thing I have written here. So this is the collector current in terms of IC, VB and VT. Using this equation, I can find out what is VB if you know what is IC, IS and VT. And of course, we know this equation also. That's fine. Now, because now we need to find the operating region of this transistor also, I need to know what is IB. So I should know what is IC also. So what is IB now? So IB is the current flowing into the base of the transistor, which is nothing but you have a voltage source here and you have a R Thevenin. And what is this voltage? Again, a voltage of VB comes into picture. You cannot escape from this, because this is base, this is emitter. There has to be some potential here. This is, I call it as VB. So I will write IB is equal to V Thevenin minus VBE by R Thevenin. So this is my IB expression. Then what is, if you know this much, okay, this is an assumed value. First assume it as some 0.75 volts and this is 0.8. So you know the difference divided by RTH, you can find this. Then find what is IC. So IC comes out to be how much? Okay, let us find out this. So how much is R Thevenin? Sorry, V Thevenin is 0.8 minus VBE, we are assuming it as 0.75 divided by how much is R Thevenin? 54.4 exponential 3. So you have a current of okay, let me just put in micro. It is you have a IB of 919 microampere. Then this is into 100, which is nothing but 9 point, okay, it is 91.9 microampere. So this is the value of IB you got with an assumption of VB as so and so, and this is IC, which is nothing but beta times IB. Now we need to verify whether this assumed value of VBE is fine with us or not, because once you have a value of IC and VT and IS, I can find out what is VB. So what is VB now? VB is equal to VT into ln of ratio of IC by IS, correct? This is VBE is equal to VT ln of IC by IS. So if I find using this what is VBE, if it is close to 0.75, then our assumption is fine. If it is not so, then we need to do some iterations where they come very close to each other. So let me again repeat. We found the value of IB as 0.919 microampere with an assumption of VB as 0.75. So the first assumption is 0.75. This is 0.8 minus of 0.75 divided by 54.4K yielded me this much current. Then what is IC? Beta times IB. Then to verify whether my assumption is correct or not, let me just find out how much is this. So how much is, okay, this is 91.9 exponential minus 6 divided by 1 exponential minus 17 whole equals ln of answer multiplied by 26. Oh, this is coming out to be 776.07 millivolt. So our assumption is 0.75, this is 750 millivolt, but I am getting 776 millivolt, because we know that even few tens of millivolts, few millivolts of change in VBE will going to have a huge change in your IC. So this is not consistent. This is not consistent in terms of both the equations. So what we have to do now is, so we assume this as 0.75, then this assumption is not correct. So the process here is, maybe in the textbook he says how to go about it. Maybe those who have seen the textbook, let me just open the textbook and that particular page. Okay, I'll do that. So you can see here. Okay, where is that? It's here. It is easy. I have. Okay, this is ebooks and this is your textbook. What you are looking at. Okay, we are recording it. Okay, page number 195 in my hard copy. Let me see how much is this. This is 190. Okay, I think I just passed it by maybe slightly lesser than that. Maybe a plus or minus change from this to that. That is textbook to the soft copies. Okay. I'll show you how it looks in the textbook so that you can just connect back to your. Okay, you're somewhere here. Okay, you're here. Just a minute. Give me a minute. Okay, let me search for that and then come back to you. Yeah, I got it here. See now, this is what you have. So this is what is Vx as 800 millivolt and R Thevenin is coming out to be 54.4. Now we are assuming this to be 750 millivolt. So that's what is VBE. So then IB came out to be 0.919 microampere, which resulted in a IC of 91.6. Okay, this is exactly the values that what we got here. See here, these are the values that we got. Then the value of VB is coming out to be 776. That's what you have here. See now, this is what is 776. So this is most important. It follows. Suppose if you take this as the value of VBE in this expression. Now if you just substitute this back, because when you started initially you took it as 0.75. If you now take it as a 776 millivolts, then the IB comes out to be this much. So when IB comes out this much and IC comes out this much, this is a still large fluctuation. So you had earlier 0.9 something as your 0.91 microampere as your IB. The IB suddenly reduces. So now what is to be done? It follows that VB reduce. Okay, VB has increased. VB with an assumption of 750 millivolt. If you start, it is ending out that okay, VB has to be more. Then assumption is not correct. So then you got this value. So then actually what happens here is it actually goes this way. So in the textbook he says, see here, we begin. So we begin with the value of VBE. Okay, this is a guess. This is what you have a guess now, 0.75. Then the iterations then follows the sequence. You assume VBE, find IB, find IC, then you re-examine the value of VBE, then find IB, IC, and then VB. This continues. So let me just do that for you and try to understand what the entire process here is. This is not confusing. Of course, maybe you might have not done this much analysis in the earlier cases. That's why it is bit finding it difficult. See now, I have done it here. You can just have a look at how I have done it. See here, this is how I started. Because this is how it goes. You assume the value of VB, find the value of IB. How do you find the value of IB from VB? You have this expression. V Thevenin minus VB by. So I got the value of IB. Then you find the value of IC using this. again refine the value of VBE using this equation. You can see this is already the first iteration. So after first iteration, you got the value of VBE as 776. If you put 776 here, then you got the value of IB as this. So for that IB, this is the value of IC. For this IC, you have this VB now. This. Okay, now VB has changed. You can see IB has slightly varied. So now it is this. If you just keep on doing this, can you see that fluctuation is too much? Can you see it is from 91, it is going down to 41 micro, then 41 micro to 79 micro, then you can see it is 51, then it is 71, then you can see 55. Can you see from iteration to iteration, the separation is keep reducing. Ultimately, you come to a point where they almost comes very close, So then, ultimately what happens is you come to a conclusion that a VBE of 766 millivolt and a IC of 63.3 microampere will going to settle down. See here in the textbook also you can see, upon doing all these iterations, here, it follows IB is equal to so that's your first value. So this is first value, next it is second value. That's what you can see here. So in the simulation, okay, in my calculation also it is same. So in the textbook he just gives only the final values. You can see this is how you got it as 63 microampere. Can you see this is coming out to 63 here? Can you see it is 63? So this 63 came after so many iterations. Now you can see after this comes, it hangs around 63 microampere. So this is what is called as number of iterations, so that your assumption of VBE, which started with 750 millivolt, will settle down at 766 millivolts. That's what is the iterations required. Of course, we don't expect you to do all these things in the examination, but the thing is, okay, maybe when we actually started, we assumed it as 750 millivolt. You may on paper design it is fine, but you'll not be getting this current. So if you actually do the simulation, you'll not get this current because this is an assumed value. You'll not get this much current, but you'll actually get this much current. You'll get 63.3 microamperes rather than 91.9 microampere, because this is an assumption which is not consistent, which is not true. How did you make this happen? This made happen because you made number of iterations relating IC to IB as well as to VB. IC is now related to both parameters, not only beta and IB, it also depends on VBE of the transistor. So now that's what is, suppose if you want me to do it for a few values, let me just, of course it is, once you have 776, you can see here, let me just keep on ticking this. Of course it's worth doing all these things. If it is 776, what I'll do, now it is VTH minus so and so. So it is now 0.8 minus 0.776 divided by 54.4 exponential 3, because it is 54.4 kilo ohm. Can you see the current is coming out to be how much? Okay, let me just do 0.441. Can you see it is 0.441 micro multiplied by 100 is my IC, which is 4. Okay, I had to do. Can you see it is 44.1 microampere. So this is my IC divided by IS. 1 exponential minus 17 is my IC by, this is IC by VT. ln of this. So ln of this answer multiplied by 26. Can you see this comes out to be 756? That's what is 756.99. Then use this to find IB. So that is minus 800 divided by, I'll just take out this minus sign, divided by minus 54.4. Can you see now it is 0.79 microamperes. This is 0.79 microampere. That multiplied by 100 is 79.1 microampere. Of course, micro is missing there, microampere. Now this into 1 exponential minus 6 divided by how much? It is 1 e power minus 17. This is your IS. ln of answer multiplied by 26. Can you see it is 772.16. See, now it requires almost 8 to 10 iterations until you get a consistent or constant value of 63 milliamperes. 63 microamperes. It will be surprising to see when we actually do the simulation with these values of resistors, that is as per this calculation, as per this circuit, will exactly get those currents. So this should be 5K. Let me make it 5K, and let me have one more resistor. How do I have resistor? Put a R here. Then okay, I think there are two resistors. Let me delete one. How to delete? The backspace, or you can see now this is fine. Okay, I'll put this. I'll do the wiring. This is going to ground. Okay, this should be 2.5. And what should be this? This should be 170K. Dear students, I want you people to do these ones. So by merely seeing this will not help you. Okay, seeing will going to, you please understand what I'm trying to say. If you want to thoroughly master this, you have to do it once, and not only the calculation but also the simulation will make you very, very comfortable. Now I can see I'm done with the connections. I will say run. Let me just run it again. What happened? I'm running now. See this, I want to see this current. So I want to see this current. Can you see how much is the current? Okay, this is, just a minute. Okay, let me take this. Okay, let me. Okay, how much is my base current? Base current is not important. Okay, my IC should be 63 point something. No, see now how much is this? It's almost there. 63. That's what is the expected current. What we thought here. Can you see it is 63 microampere? Are you not getting very close to that? How much is this? Can you see it is 66? Hardly 3 microampere difference. How much is VB? Very interestingly, VB, if you see this, it will be close to. Of course, whatever voltage that you see here will be 0.8. Whatever voltage that you see here is 0.8. Can you see? Okay, now this is, sorry, that will be VBE. VB will be 0.766. That is this voltage. What is the voltage you will also see? So this is VB will be close to 766. This is approximate value. So 766. I think you'll be getting very close to that. Can you see it is 763? This is your VB, and this is IC. This is IC. So this is IC value. This is, you can see it is far away from that 750 millivolt, and this is far away from that 90 microampere when we initially considered. Can you see, when we initially started, was it actually the first assumption was 0.750 millivolt, and this IC was supposed to be 91 microampere, but when you actually simulate it, it is nowhere close to 90 microampere. It is close to the expected iterated value. How much is the expected iterated value? The iterated value is close to this is 63.3 microampere. The voltage is 766 millivolt, which is very close to the simulated values. Can you see this is your simulated value? Of course, in simulation you got this value. This is the current, this is VBE, and this is how you can feel comfortable. Okay, it is not too far away from my expected values. Now it's very important that the beta F and IS have to be specified for the BJT model. Of course, there is one more. You can pick a transistor from the library. You can see this. Suppose if you take this as a transistor, can you see all these parameters are given? So this is a transistor. Let me show you all. Can you see this is dot model Q2N 2222 NPN. So this is the model name. This is NPN transistor. Can you see IS 1 e power minus 14? In our case, we have taken it as minus 17 because in the textbook it is minus 17. I have taken the same thing. Can you see this beta F 200? There are so many other parameters, VAF, IKF, XTB, and you can see the junction capacitances. So all these stuffs are there. So we have not considered all those. We have considered only two parameters, that is IS and beta F. IS corresponds to leakage current between base and emitter. It is not ICBO. ICBO is between base and collector. This is between base and emitter. Because emitter is heavily doped, leakage will be lesser. So you have 1 into 10 power minus 17 is the value of IS. Of course, this will slightly, maybe in Q10 222 it is 10 power minus 14. This is a range of minus 14 to minus 17 will do. So this I took it as per the textbook. Okay, you can see textbook says you take the value of IS as, that's what is there here. Can you see this is the value of IS? IS is 10 power minus 10 to the power of minus 17 amperes. Okay, now you're trying to jump into the real electronics and trying to understand the beauty of it and the complexity involved in designing the circuits. So of course, only in BJT you have this much complexity. When it comes to MOSFET, it is very straightforward. So this much number of iterations are not at all required. So that's why in modern electronics, MOSFET are ruling the entire industry in terms of circuit design. Of course, BJT is used only at the last stage where it is required to have a larger current or operating speeds. Of course, large current as well as speed, if it is essential, then they go for BJT, which we say it as BiCMOS. Along with MOSFET, you have BJT, that is bipolar MOS transistors, that is BiCMOS, which you may be exposed in your higher studies, in your higher semesters. Thank you.